Hello, and welcome to my talk about the role of simulation in the industrialization of additive manufacturing. My name is Nicholas. I'm a research engineer at Siemens, and in this talk I would like to talk to you about the challenges in designing structural components using additive manufacturing and the role that simulation can play in trying to resolve some of these issues. In conventional fatigue analysis, a knockdown factor approach is probably the most often used solution to account for a specific material condition. In this equation, for example, Ka could represent the effect of surface roughness, while Kb accounts for heat treatment, and so on. You can define as many knockdown factors as you need to account for the specific material condition of your component. Although this is a simple method to use, when we try to apply it to additive manufacturing, we see that it doesn't work very well. For example, the picture on the right shows some fatigue data for an additive manufactured stainless steel. It shows a stress amplitude that will lead to a lifetime of 100,000 cycles, and how the print orientation of the coupon affects this stress amplitude. In the graph, you can see the results for 4 different material conditions, going from an as-built condition to a hipped and machined condition. If a knockdown factor approach would be suitable for this material, then we should see that the effect of print orientation is independent from other parameters such as surface roughness or heat treatment. However, looking at the test data in this graph, we see that this is not the case. The effect of print orientation is different for the as-built condition compared to the hipped and machined condition. And the difference is not just a constant scaling factor, it's even a different or an inverse trend. So clearly, for this material, a simple knockdown factor approach will not work, and we need material models that can account for more complex interactions between the different factors. On top of that, there is an added complexity in additive manufacturing that the material condition is no longer constant throughout the component, but becomes a local parameter driven by the print process and the geometry of the component. Therefore, for additive manufacturing, fatigue cannot be seen as a separate topic, but it is actually the result of a complex interaction between manufacturing, design, materials, loads, environments, etc. The challenge for proper AM design can then be split into 2 separate topics. On the one hand, there is the challenge of predicting the local material conditions in an AM process, accounting for the specifics of geometry and process parameters. On the other hand, there's the challenge of building a more advanced fatigue model that can account for these locally varying material conditions in a proper way. The first step in predicting the local material condition is to perform a so-called process simulation. In that simulation, we predict the thermal histories, the distortions, and the residual stresses in the component, starting from the process parameters used during printing. Predicting distortions is important because they can affect the orientation of in-service loads, as well as generate interfacial stresses when the component is mated to another component. The picture on the left shows a distortion prediction as well as a deviation analysis where the prediction is compared to an experimental measurement. For this specific component, you can see that the average deviation is less than 1/10 of a millimeter. The residual stresses in the component will act as a mean stress, and we know that in terms of fatigue performance, mean stresses are very important to take into account. Finally, thermal histories will drive the microstructural properties of the material, and those again have a strong impact on the fatigue performance. The 2 pictures on the right show the results from a thermal analysis, and the picture in the middle shows that to get a good view of the thermal history of a component, you should not only look at the single component, which would give you the red dotted line, but actually you have to take into account all components in the build chamber to get a good representation of the thermal history of your own component. Once the thermal history of the component is known, further local microscale simulations allow you to predict microstructural features such as phase fraction or grain structure and the occurrence of voids and other defects. The animation on the left shows a microstructural simulation for a specific scan pattern, while the pictures on the right show the prediction of porosity and a comparison to CT data from an experimental sample. It is known that all of these features can affect the fatigue performance of the material, and therefore it is important to be able to predict them. A final example of calculating the local material conditions is predicting the surface roughness of an additive manufactured component in the as-built condition. For additive manufacturing, surface roughness is no longer a constant, but it's driven by a combination of the process parameters and the orientation of the surface relative to the build direction. For complex geometries, FE analysis allows us to calculate the orientation of the surface in each point of the model and convert this to an equivalent roughness. The pictures on the right show two roughness predictions for different definitions of the build direction. As you can see, in each of the models, the surface roughness varies throughout the part, and between both models, the location of high roughness areas and low roughness areas varies with the definition of the build direction. The previous slides have all focused on how FE can help us predict the local material condition in an AM component. The next challenge is now to define a fatigue model that is able to take into account all of this extra information and provide a more accurate estimate of fatigue lifetime for an AM component. We know that knockdown factors will not work for AM fatigue because there's a complex interaction happening between the different conditions. We could consider making a more complex form of a knockdown solution, but those solutions would lack flexibility to be applicable for multiple materials. Another solution is to look at multidimensional interpolation, but that will quickly lead to excessively large dataset requirements and poor performance and overall prediction capability. So the question remains, how can we develop a suitable model for AM fatigue that will work, first of all, on scarce datasets because fatigue testing is expensive, and that does not require many a priori assumptions because we want it to be applicable to many different materials. It should also allow us to account for many influencing factors like roughness, porosities, material orientation, or any other influencing factor that is relevant for your specific application, and they should be flexible enough to work on many materials. In our approach, we use the Gaussian process regression to model the fatigue life. The animations at the bottom of the screen illustrate how such a regression works. Starting on the left, you see two variables, y1 and y2, and imagine that they represent a lifetime of a coupon in a certain material condition. On top of the two variables, we also define a covariance matrix, which defines how the two variables are related to each other. In this case, we chose a positive correlation, meaning that the value of y2 moves up with the value of y1 and vice versa. The animation on the middle of the screen shows you the same condition as on the left of the screen, except that the value of y1 has now been fixed to be exactly 1. This could, for example, be the case when you tested the material condition y1 and you know the outcome of that condition. What you see in the middle of the screen compared to the left side is that the possible solutions for y2 have now been severely restricted compared to the situation on the left. The same concept can be extended from just 2 variables to 20 variables, as you see on the right. In this case, variable y1 and y2 have been fixed, and all other variables are free, but have to respect the covariance matrix defined. In this case, you see that for variables that are closely correlated to the fixed variables, the potential solutions are limited. On the other hand, variable y20, which is very loosely correlated to the fixed variables, can take on a lot of different values, and there is not a strong correlation with the fixed data. The same concept can actually be extended even further than just a discrete number of variables and can work on an infinite space. In this case, we no longer define a covariance matrix, but we define a covariance function. This concept can then be applied to model the fatigue behavior of AM materials. By picking the right covariance functions, we can define trends that we expect to see between variables. And by feeding it training data, we restrict the feasible outcome of untested data points. This is similar to what you see in this animation. In this case, the first 2 points are training data, points or conditions for which you know the fatigue life, and all the black points are the actual potential solutions for untested conditions. The outcome out of this Gaussian process is then a probabilistic estimate of a condition that has never been tested. It gives you an indication, first of all, of the reliability of the extrapolation and of the scatter in the test data. To conclude this presentation, I wanted to give a short use case example of an automotive gearbox bracket. We performed a stress analysis indicating 3 potentially critical areas in the component, and we used the enhanced fatigue solver which I described to account for the local conditions in each zone and to help predict lifetimes and failure locations. The SN curves on the right of the screen show the predicted material performance in the different zones, taking into account the local material condition for those zones. As you can see, the material performance can change significantly from zone to zone and depending on the assumed machining in a certain zone. On top of that, if we compare the predicted fatigue performance to fatigue performance that you could find from literature, we see that again there is a large difference. Starting from the SN curves on the previous picture and compensating for notch effects, as well as rescaling to component load, we get a picture on the right. Although we started with zones that had very similar stress levels, this picture illustrates that by accounting for the local material condition in each of the zones, we get very distinct fatigue performance in each of them. On top of that, the dotted lines show the predicted fatigue lifetime if we would have relied purely on literature data. In both zones, the literature data is 1 order of magnitude higher than what we predict with our models. In summary, this presentation has shown how process simulation and local property prediction can help in predicting the local material conditions in an additive manufactured component, and it has shown how a Gaussian process can be used to develop a fatigue model for an additive manufactured component with many fatigue influencing parameters. Finally, the application to a use case has illustrated the risks involved when relying purely on literature data to assess the fatigue performance of an AM component. At the moment, testing is ongoing on this use case to validate our predictions. Finally, I would like to thank the partners and funding agencies that have made this research possible, and I would like to thank you for your attention.